coming to the other course as usual. So we are coming back to the Fourier series. So in the last presentation I introduced the fact that if you are having a orthogonal system of functions, so I remind that we are working in the space S0 of piecewise continuous functions, or perhaps we also want to have some piecewise continuous derivatives. So it means that up to the order k, the derivatives not only exist but are piecewise continuous. So it means that all the previous one up to k minus 1 have to be completely continuous, right? Because every differentiable function is continuous. Well, except there might be still the jumps, right? So if we, well, I don't have to go into details here. So having such an orthogonal system of functions then in this space, so any system like that, we mentioned, for example, the Legendre polynomials, we can form something similar as power series, except instead of the monomials Fn, there will be a linear combination of our orthogonal system of functions, and there are countably many of them, and simply the partial sums of this series will be some approximations built on the best ever possible linear combinations of the given functions in the order as we get them. So an orthogonal system of functions is a sequence of functions which are mutually orthogonal. And we saw that in terms of L2 distance, which was the L2 distance or the L2 norm, was defined as the square root of the integral from a to b from absolute value of fx square dx, right? So that's the L2 norm. The distance is then, of course, the norm of the difference of the two functions. And it's not easy to decide whether such a series will be convergent. It's not easy to see whether it will be converging or not in the L2 distance norm. And we saw that there are the Bessel and Parseval inequality and equality, which tell us a little bit more, right? But still, it's quite vague, and the example, as I told in the very end of the last presentation, if we, for example, take only the odd monomials and build the Legendre type polynomials on them, then we get a orthogonal series which will possibly be nicely approximating all the odd functions, but definitely not the even ones, right? So we have to take this in with care, and also it's not that easy to find an orthogonal system, right? It is, because we can take any sequence and make the Gram-Schmidt orthogonalization up to infinity, but this is possible in principle but difficult in the real situation. But there is the most original orthogonal system, which was the beginning of the Fourier series and comes back to Fourier himself, and that's the system built of the periodic functions sine, cosine, with smaller and smaller periods, right? So this is something really nice, and of course it comes with a lot of questions, because someone can tell you, let's take this orthogonal system, but we should perhaps, as mathematicians, we should check its orthogonal. So in a moment, so a bit later, I will show you that it really is. If you couldn't continue before knowing it, you can just try yourself. It's a quite elementary exercise on integration by parts, which shows that this is really an orthogonal system. But let's first come to the formal definition what a periodic function function is. So if we have a real or complex valued function which should be defined on the entire R, so we call it a periodic function with period t, which must be some real bigger than 0, if simply shifting the argument by t does not change the value. So that's the periodic function. And of course the cosine and sine, they are of this type, right? So they look like that. And if I, that's strange, what did happen? Strange behavior. If I do the wiggling long enough, it disappears then. So this is just the one of them. So you see I started with 0, so it's the sine. If I would just go with the bigger n, then it's the same, except it's just wiggling much faster, right? And it makes the same thing, right? So this is the periodic functions. And note that if we make an integral over a periodic function, then the interval we are integrating over has, well, if it's an interval of the length of the period, then it doesn't matter where I start. So it means that here I can just take the interval from anywhere to anywhere, like going from here to here. If, well, it's the period roughly, no, it's not long enough. So if I go from here to here, so it must be the same as if I shift it and start here and then here, right? So the integral will be simply the same. So that's computed here. And also, just what's easy is that if I take the integral of sine nx squared, then I can compute how much it is, and what you get is pi. If it's over the period 2 pi, so except the 1 will be, so if n is 0, then it's sine of cosine of 0, constant 0, and that's constant 1, and then there it will be 2 pi, right, the square. So therefore in the definition of the Fourier series, the real Fourier series, the classical one, so I get the A0, which would be just the integral of 1 over the period long interval, and I divide it by 2, so divide it by 2 pi to normalize it. So this will be the A0 square half, and then the rest is, I have the A's which come with the cosine, which is the even part of our orthogonal system, and then I've got the B's which come with the sines, and they are the even part, they are the odd part of the orthogonal system. And this is called the Fourier series of a function g. You see g is just here, and this is the scalar product computing the coefficients. So that's how the abstract Fourier series were defined. We just make the difference between the even and odd part, taking it separately for the sines and cosines, and call the coefficients not Cn for everybody, but An and Bn. And then the coefficients are called the Fourier coefficients of the function g. So this is the classical Fourier series, and it always looks in this way. Well, I mean, here in the shaded box, I wrote it for the period 2 pi. If we want to start with some other initial period, so the beginning, so what we start with, then we can just take any length t of our period, and that could be taken as the time for one revolution of the object moving around the circle, right? So the period, the standard period, the most standard series is 2 pi, because that's the length of the circle. So if you go with unit speed along the circle, you will see why I'm talking about the circle now, so it will come back in a second. Then then it's the time you need to come around and revolve and start again from scratch, and you are just moving on and doing it longer and longer. So if we want to take time t to come back over all the one unit circle, then the constant speed would be 2 pi over t, and that's the so-called frequency. So then we simply have to replace the nx in our definition by omega nx, right? Omega is just the 2p over t, so the relation between the standard period and the wanted period. And then of course the Fourier series will be of this kind, and the Fourier coefficients will be, here you will have the t as the length of the interval, you have 2 over t for the a's, with the exception of a0 where it's just coming with a half, that's the coefficients, and the same with b, 2 over t, right? So that's the specification for all the things. Right, and now we are coming why the circle, because the circle, the unit circle, is best viewed as the unit circle in the complex plane. And you know that the unit circle is parameterized this way. So omega is how far we are, so unit circle can be parameterized this way, right? And then so if it's fixed omega, we have to come with t to the period, and it gives you back to the initial situation. And then just it's quite straightforward to compute that if you take these functions where you have different m and n, and then you take one with plus and the other one with minus, then of course you know that there is the formula for the exponential, it's this, and it's not difficult to check. Well, it looks like if it was real and you just take the primitive function, but it's easy to check that it works for the complex version as well. So you get this result, and clearly it's 0. So you see that for m different n, you see that the cosines these things are orthogonal, right? So we definitely get an orthogonal system of this kind. So notice that now instead of having 2 of them, the sines and cosines with multiples here, so the n times the same thing. So I will just move back a little bit, right? So this things, we simply have it this way, and instead of having them separately, we have them together, but we have them from minus infinity to plus infinity. And you see that if you take the 2 which are with the minus, so you can either add them or subtract them, and up to the multiple by I, you get exactly the sines and cosines as usual. So this should be an equivalent orthogonal system, right? So if we allow, even for real functions, if we allow to compute these complex numbers, which the electrical engineers always do, because you see they always like to have it this way, so it's complex, and they separate the even part being the real part of the signal and the odd part being the imaginary part of the signal, and this helps them amazingly. So you will see it on the Fourier series, and then later on the Fourier transform why this is the case. So if m equals n, then of course what we get is 2 pi, right? So we always get an I think, and then of course if you rewrite what we know already, so from the orthogonality of this system, which we checked so easily, we immediately can deduct that this will be also orthogonal. Yes, so the original system. So this is just the verification that the original orthogonal system was orthogonal as well. So now we are at a situation that for a real or complex function f, and we move on an interval which goes from minus t half to plus t half. Why not? That's just half of the period will be minus, half of the period will be plus. And we compute the Fourier coefficients, the complex Fourier coefficients, by the same form as we have it in the abstract approach, right? So the f is put into scalar product with e to minus I omega n t, because it has to be conjugated, right? So the other guy has to be conjugated, and to conjugate, moving on the unit complex circle means you just run around the same circle in the opposite direction. So it's exactly this, right? Of course, if the function f was real, then you can see that the or even if it wasn't real, so if it was complex, so the relation between the original presentation of the Fourier orthogonal series via the sines and cosines and the complex version of it is that the Cn with positive n are these guys, whereas the Cn's with negative coefficients will be these guys, right? Because the An's and Bn's exist only for the positive n's. And so if the f is a real valued function, then of course you see immediately that the Cn and C minus n are complex conjugated, because then the An's and Bn's will be real, right? But the formulae hold all the time. And so we can express the Fourier series in this nice form, right? So this is a very useful form of the Fourier series for what we are doing. And now we are coming to the ultimate results in our presentation. So this is the complete answer for what's happening with the Fourier series in the case of dealing with functions which are from S1. So we need piecewise continuous functions with piecewise continuous first derivative. So remember, in the points where the function jumps, there still have to exist the one-sided derivatives, and they can be jumping at these or other points, right? So the derivatives have to have one-sided limits everywhere and exist in this sense everywhere. Right, so what's the result? So first of all, we get an ultimate answer about the pointwise convergence. So whatever f we take, which is piecewise continuously differentiable. So we know that the Fourier series always converges pointwise. So it always converges pointwise. That's a great thing to know. And we know to what it's converging. It's always converging to the average of the left and right limits. So if f is continuous, then it converges to the value of f. If f is not continuous, so if f was something like this, say, then the Fourier series would just converge to everything. So in every point it will converge to these guys, but here it will converge to the middle of the jump, right? So that's the result. It's very nice. It's the best you can hope for, right? Moreover, if the periodic extension of f, right? So you have to be careful with that periodic extension of f. So you can imagine. So for example, if I take something like this guy and take my period, my interval to be this, so this is A, this is B, then periodically extending it will be continuous, right? So if the periodic extension of f is continuous, so not necessarily having continuous derivatives everywhere, right? So you see here it has got different derivative from left and right. Still it fulfills this thing in 2. Then that not only by 1 it converges pointwise to the value of f everywhere, but on top of that it always converges uniformly. So you have got the same nice thing as with the power series. So it just wherever it converges uniformly. So for nice functions it converges uniformly. And the third point is that the L2 distance always converges to 0. So it always converges at L2 to the limit which is originally there. So you see, in that sense the original Fourier series are behaving absolutely the best ever way you can imagine on the space of the piecewise differentiable functions. So this is the ultimate result, and I'm afraid the proof is quite complicated, so I will not give the proof in the presentation. I will just make some glimpses towards that, but I will not tell much. And now I stop the presentation and will come back with some examples how to use it and how it works.